with this then. And let's see, I might want to, let me dim the lights or something. Can you guys see? So, okay, so what we're doing is we're doing derivatives. And so to begin with this one, we've learned all those different derivative rules then primarily. Okay, so first thing we want to do at this stage is you want to go ahead and multiply this one out. Okay, so if I do this, just go ahead and do a distributive property, and then we'll do the derivative. We're kind of at a stage where you have to multiply, then differentiate. So I'm going to start by just doing multiplying out. Remember, you add the exponents when you multiply variables, so that's going to be negative 2x to the 13th. Okay, now you're going to have negative 2 times negative 1/2. The 2's cross out and you get a positive. So that's going to be positive x to the 4th. Again, we're doing 3 plus 1. And then negative 2 times 20 is minus 40 x to the 3rd. So you want to make sure that you're totally solid on the algebra aspect of everything. Don't make mistakes when you multiply stuff out. Okay? All right. So now we do the derivative. And that's what we were working on last week. So remember, we have the power rule, which is what all these things are going to apply then. So you're just going to do the power rule on each one of those things right there. Okay, so bring the 13 down, multiply it by negative 2. That gives negative 26. What happens to that 13? Where does it go? Goes down 1. Okay, so that goes to 12. Same thing with this. The 4 comes down in front. That would be 4x to the 3rd. Bring the 3 down, multiply it by 40 to get negative 120. X to the 2nd. Okay, so most of these problems like this you'll be able to do in your head. So that's your derivative. Okay, that's using the power rule and the different rules that we learned last week. Okay, everybody follow that pretty good? Okay, all right, now when you do this next one, you have to multiply this out first. Okay, you can't bring the 2 down and do stuff like that. I got it working. Okay, it took me a while, but I got it. Thank you. Okay. All right, so g of x, what we're going to do on this is just multiply this by itself. So you want to go ahead and just FOIL that out before you do a derivative. A little later on, you're probably into this week and next week, we'll learn a different way to do this by something that's called the chain rule that makes it a little faster. Okay, so go ahead and multiply out. So you'd have 2x times 2x. It's 4x to the 2nd. Do your outside term, so that's going to be plus 10x, do your inside term, which is 10x, and then 5 times 5, 25. Now, you don't have to do it that way. You can do this in your head if you want to. So that's 4x squared plus 20x plus 25. So you've multiplied it out, and now you're ready to get the answer to the derivative, okay? And this is a problem you should be able to quickly do in your head, the derivative, okay? So what's the derivative of 4x to the 2nd in your head? 8x. How about the derivative of 20x? 20. Be careful about that. Remember that one, if you have a linear term, if you have just x, the number in front's the slope, therefore it's the slope of the tangent line. And then what's the derivative of 25? 0. Now you don't have to write that on there, but just to emphasize, the y part of that, you would have 8x plus 20. So you have a quadratic function, and the equation, or the function that's a derivative, is linear. Okay, it goes down in one term. Okay, how's that look so far? That should be relatively simple. Okay, the next one's a little harder because you got square roots in it, but we're going to take exactly the same approach. So what you're going to do on this is go ahead and just multiply it out. Okay, you can do this totally in your head if you want to. The first term, you're really doing the square root of x squared, so what happens to the radical? Goes away. Okay. Outside term is going to be negative 2 radical x. Inside term is going to be plus 5 radical x. And then the last term is going to be negative 10 like that. Okay? So that's going to give g of x equals x. These are like radicals, so you have 3 of those. And then I just bring down the minus 10 like that. So that's multiplying out the derivative. Okay, does that look okay to everybody? Okay, what do I need to do with that square root of x before I do a derivative? Change it into a 1/2 power. Good. Okay, so you got to do that. So from here, I'm going to go ahead and just write this as g of x equals x plus 3x to the 1/2 minus 10. Now we're ready to do our derivative, see, okay? All right, so what's the derivative of x? 1, good, the number in front. Okay, the next one, do the power rule, so you're going to take the 3 times a half, and then you're going to subtract 1 from the exponent. You can do that in your head. I don't mind if you do that in your head, but you're subtracting 2 halves. I'm using a common denominator. Then the derivative of 10 is 0, so you don't have to write the 0 there, okay? So now if we clean this up, we're going to get g prime of x is 1. That would be 3 halves when you multiply that straight across. Then that would be x to the negative 1/2. So that would be one way to write that derivative, okay? So I want you to be able to write these things in different forms. That's certainly one good answer. Another answer would be 1 plus 3 over 2 radical x. And you can do that in your head. I'm just bringing the negative 1/2 power down to the bottom and taking it into a radical. Okay, everybody follow that okay? All right. Okay, so these are the derivatives that we're going to do this throughout the rest of the semester. This will be even a part of bigger problems, which we'll get into today. We'll get into the ones that are a little meaner. Okay, any questions about those then? Okay. All righty. Okay, so let's do some quotients now. And what I want to look at on this a little bit is when you're doing a quotient, you cannot just do the derivative of top and bottom. Now, don't write this down, but just pay attention to this, because a lot of times I see students, they'll go through and they'll get the derivative of the top, which is 24x squared minus 8x plus 1, derivative bottoms 2. It does not work, okay? What we'll learn in the next section is something called the quotient rule. So anytime you have a fraction, you can't just do derivative of top and bottom. It does not work, okay? So what you have to do instead of that, you have to go through and kind of split it up algebraically before you even do the derivative. So what I'm going to do is we're going to split it apart like this. Okay, we can just do the top over 2x, each term over 2x, then simplify, and then we'll do the derivative like that. So all you're doing is just taking the fraction and splitting it apart into 3 fractions. You can always do that. Okay, then what you want to do is you want to simplify this. So if you simplify this, what does this simplify to in your head? 4x squared, right? Okay, and you got x to the third over x to the first. One of the x's cancels out. You're just subtracting exponents. What's the next one? Good, minus 2x. What's the next one? Good, it's a half. Okay, like that. So that's how you would simplify that. Now you're ready to do the derivative, and you should be able to do this derivative in your head. So the derivative of 4x squared is what? 8x. Derivative of 2x, what's that? Minus 2. And then the derivative of a half is 0. So then that would be the value of your derivative right there. Okay? So that's the approach that you have to take on that problem. At this stage, and even when we learn what's called the quotient rule, you would probably do it this way anyway because it's easier than the quotient rule. Okay? All right? So the next one is kind of the same idea. You cannot just go through and do derivative of top and bottom. You have to simplify. So how do you think you would simplify something like this?
No, just split it.
You can factor, right? Okay, that numerator is a factorable polynomial. It's a difference of 2 squares. So it's no different conceptually than having, like, if you had x squared minus 1, the way that factors is x plus 1, x minus 1, right? This is the same basic strategy. So what I'm going to do is I'm going to write this as a difference of 2 squares. And when I factor that, the first term is t squared and t squared. The second term's 1 and 1. Then you have a plus and minus. Okay, and then you have that all over t minus 1. Okay, I'm still not done. Does the numerator factor any further? Yeah, okay, here's what happens is this one factors. That's still a difference of 2 squares. However, this one does not factor because it's a sum of 2 squares. So that's a little algebra background that you're going to have to deal with a little bit. So if we do that, what we would have now is we would have g of t is equal to t squared plus 1. Now you go ahead and factor this part I've got highlighted in yellow one more time, and that's going to be t and t, 1 and 1, plus and minus like that. Then I've got all over t minus 1 like that then. Okay, you guys see how that factors? Okay, there's factoring issues in this class that some students have, and it's a big part of what you do in calculus. You factor up stuff all the time. So what happens now is these things cross out. Okay, so let's write what we're left with now. We have g of t equals t squared plus 1 times t plus 1. So we've simplified it. Now, at this stage in the class, the only choice you have is to multiply it out, like by FOIL, then finally do your derivative. Okay, does that make sense? Okay, so we've got all this algebra going on. So let's go ahead and FOIL this. So the first term is t to the third. Outside term is t to the second. Inside term is t. And last term's 1 like that. Okay? Now we're finally ready to do the derivative, which hopefully you can just do in your head. What's the derivative of the whole thing in your head? 3t squared plus 2t plus 1. Good. Okay? All right, so this piece right here, by power rule, is 3t to the second. This piece here is 2t to the first. This piece there is the number in front. You want to get totally solid on that linear term right there. And then, of course, the derivative of 1 goes to 0, so that would be your answer. So say there's a lot of work on that problem just getting to a point where you can do a derivative. So at this stage, if you have a fraction, simplify it as far as you can, and then do a derivative. Okay, because all you know is really the power rule. Okay, and the derivative of a constant 0, that's about all you know so far. Okay, okay, let's take a look at this example 3. And again, we cannot just do derivative of top and bottom. We have to algebraically simplify this in some way. All right, so what do you guys think on this? What's something I could do to simplify that one? Yeah, the conjugate, right. Okay, you kind of get to a point where you start seeing that conjugate a lot. You see square roots, you have two terms. So what would be kind of logical, and we've seen this before, is just multiply by the conjugate. So let's multiply both the top and bottom by square root of x plus square root of a. And we'll kind of see where that leads us now. Okay? All right. Now, what you want to do with this is don't do anything to the numerator, because what you want to do is you're hoping something cancels. Okay, and if you want something to cancel, you need to leave it in a factored form. So I'm just going to leave the numerator the way it is. And then I'm going to multiply out the denominator. Now, we've done conjugates enough by now that hopefully you can do that in your head. I'll just write the step. The first term is square root of x squared, so that becomes x, right? And then the last term is minus square root of a squared. And remember, when you do a conjugate, the inner and outer, what happens? They cancel. Right? Okay, so you don't have to show all those steps of FOIL, because you know that's going to happen anyway, see? So what I'm going to get from here is this. I'm going to have x minus a times square root of x plus square root of a over x minus a. What happens? Okay, cancel. Okay? All right, so that means that what we're left with is square root of x plus square root of a. Now from here, we're going to go ahead and do the derivative. So we're going to do, I'm going to use this Leibniz notation this time and just say dy over dx. That's how you write, that's the Leibniz notation for doing a derivative with respect to the variable x. So if I do this, you would probably want to write this as x to the 1/2. You could write a to the 1/2 if you wanted to, but it doesn't make any difference, okay? So the derivative of x to the 1/2 by power rule is 1/2 x to the 1/2 minus 1, like that. Okay, what's the derivative of a to the 1/2?
0.
0. How come?
Constant.
It's a constant, exactly. That's a part of the problem. It says a is a constant, so if that's a constant, then that derivative is going to go to 0 like that. So it looks like you would get 1/2 x to the negative 1/2 like that. And that would be one way to write the derivative. The other way to write the derivative is 1 over x to the 1/2 or 1 over 2 radical x. You don't have to worry about rationalizing denominators. You can leave the radical in the denominator if you want to. Okay? Okay, does that look okay? Okay, so see, you get into algebra background a little bit. You do a lot of factoring. You work with radicals, conjugates, so it's just, and it's going to get a lot heavier than this. Okay, so I always tell students you will get really good with algebra after you take calculus. Okay, that's usually when your algebra skills start developing, getting strong. All right, so let's move to the next thing here. So I'm going to give you guys a little time to do these, like about 5 minutes or so. Let's try about 5 minutes and see where you get on these, okay? That's just one of each kind of thing, basically. Number one, you want to think about splitting the fraction, then doing the derivative. Number two, you want to think about rationalizing like we did. And the third one, think about... Okay, so when you do this one, you want to do this. Now, you can do the simplification in your head. You're just doing 15x to the third over 5x minus 10x squared over 5x plus 8 over 5x. You've got to be careful about that last term and how that works then. Okay, so when you simplify this, you would have h of x, 15 over 5 is 3, that's x squared. Then the x, that would be 2x. Okay, now the thing on this one is, I don't know if everybody got this, but you need to. The only way to differentiate that is to move that to the top and make that 8/5 x to the negative 1. You have to. Okay, that's the only way you can do that. I think some of you may have overlooked that one, so you got to make sure that you got that. Okay, now the derivative is pretty easy to get. So now you're going to have 6x minus 2. Okay, don't forget if you have a linear term and x the first, the number in front is your derivative. Then you bring that down, so that would be minus 8/5, then x to the negative 2. That's good enough. I'm just going to leave the answer that way. Of course, you could make the exponent positive by bringing the x squared down if you wanted to. Okay, does that make sense? Particularly that last term. That's the key.
Why did that become negative?
Which one? This one, because I have to move it to the top. Okay, so if you have an x to the first, when you move that to the top of the fraction, and I might not have wrote that in the best way, it goes like this. It's really 8x to the negative 1 over 5, because I'm moving it to the top. Anytime you change positions of expression is in the fraction, the exponent changes sign. And you have to do that in order to do that power rule. Okay, has everybody got that? Okay, that's crucial. Okay, the next one, let's see what we're going to do on this one is rationalize the denominator. And if you got through this effectively, then you probably would have got the right answer, okay? So when you do this, you're going to have leave the numerator factor. Don't multiply out the numerator because you're hoping something will cancel. It's designed that way, okay? Now the denominator, you want to just do this in your head. Square root of t times square root of t is what? T. Negative 1 times 1, negative 1. Okay, if you got a conjugate, you want to do that real quick and efficiently. Okay, that crosses that out, so that means that h of t is going to just be left with square root of t plus 1. Okay, now what do you need to do with the square root before you do a derivative? Right, you got to write it as a half power, so we'd have h of t equals t to the 1/2 plus 1. Okay, now you're ready to do the derivative and get your answer. So h prime of t, bring the 1/2 down, is 1/2 t to the 1/2 minus 1. And then, of course, the derivative of 1 is 0. So you would get h prime of t equals 1/2 t to the negative 1/2. And I'll just leave it at that stage right there. That's good enough. Okay? All right, does that look okay? Okay? All right, now the next one, all you could really do at this stage, and even when we learned the quotient rule, which we're going to look at a little bit today, you'd want to do it this way anyway because it's easier. So what you should have done is factored an x out of the top, and if you do that, you would have x squared minus 6x plus 8. Then you should factor a x out of the bottom to get that, to get x times x minus 2. Okay, now the other thing that you should have done is that's a trinomial that also factors, right? Okay, so you want to do that. Okay, and you can go ahead and cross the x's out. That helps. Okay, and then what we'd have from here is we'd have x and x. 4 times 2 gives you the 8. And then 2 minus signs like that would be your factoring. So after you've simplified the whole thing, you get y equals x minus 4. Okay, so you got to be totally solid on your factoring. Now if we do the derivative, what's the derivative? 1. Okay, the number in front of x is 1. The constant 4 is 0, so the derivative is 1. Okay, that's how you get it. Okay, so if you look at that problem, about 99% of it is algebra, right? That's really the way this kind of works, is when you're doing derivatives, the vast majority of it is algebra. You get it down to a point where you can do a derivative, okay? All right, so that's kind of gives you some of the ideas. Is there any question about anything going on those problems? Okay, algebra solid. Okay, that's what I'll be kind of looking out for. All right, let's do a couple of applications. I'm going to do this problem here, and then we'll kind of do the break here in the middle here. So this one is, we're going to do an equation of a tangent line, and we've done this before, but now we don't have to worry about the difference quotient. We just kind of do the derivative. So first of all, if you're doing an equation of a tangent line, the general formula that you're going to use when you find an equation line is going to be this. Okay, but the only difference is m, really what m is just the derivative of whatever that function is evaluated at whatever point a you have. A is just sort of an arbitrary number. Okay, in this case, a is going to be 4. That's where I'm wanting you to find the equation of the tangent lines at. Okay, so what we're going to do with this one is, there's 2 things you have to do, really, essentially on this. The first thing is, you got to find the point. Now, I've given you the x value, you got to find the y value. Okay, so what we have is, if x is 4, then we just need to evaluate the function at 4. Okay, you need to just plug in x equals 4 and to the function, which is this, and evaluate that. So that's going to be 2 times the square root of 4 minus 4. So that looks like that is 2 times 2 minus 4. So that's going to be 0. Okay, so what that means is we get a point 4, 0. And that's what we're going to plug into our formula for x1 and y1. Okay, so that's the first thing you got to do, is make sure that you have your points. So we've got that. Okay, second thing you want to do is you want to do the derivative. Okay, because you've got to find the slope of the tangent line, m, by doing the derivative. So let's look at f of x. Let's write that as 2x to the 1/2 minus x. Now we have to go ahead and do the derivative on that. Okay, everybody okay so far? Okay, so I have to give you an x value, and you can't do the problem if you don't have an x value, but you have to find the y value. So now we do the derivative. Okay, so I'm going to just write the 2 down, bring down the 1/2. Okay, subtract 1 from the exponent. You can do that in your head. I'm just going to keep showing you what my thought process is. And then the derivative of x is what? 1. Okay, that's a linear term, so that's 1. Okay, so what that's going to give is f prime of x. The 2's cross out, so that looks like that's x to the negative 1/2 minus 1, like that. Now I'm going to go ahead and write that in this form as 1 over square root of x minus 1. Okay, everybody okay with that? Algebra? Okay, bring it down to the bottom to make it x to the 1/2 and then change it back into a radical. Now what you want to do next is you want to plug in that number 4 right there. So what you're really doing is you're doing the derivative at 4 to find the slope of the tangent line when x is 4. So that's going to be 1 over square root of 4 minus 1. So that looks like 1/2 minus 1. Okay, you can get a common denominator, or you can do that in your head. That's 1/2 minus 2/2. So that's negative 1/2. So this thing right here is the slope of the tangent line. So I've done the 2 key things I have to know. If you're going to find an equation of a tangent line, you got to know 2 things. You essentially got to know the point of the tangency, and you also got to know the value of the derivative. And that negative 1/2 is giving you the slope of the tangent line. Okay, does that make sense to everybody? The only calculus part was the derivative. Everything else is arithmetic. Okay, So now what I'm going to do is we'll put this together. We're going to use the formula y minus y1 equals m times x minus x1. Now we just plug everything in. So you've got your 0.40. So that means 4 goes there, 0 goes there, which is awfully nice. The slope goes there, and that slope again was the derivative. Okay, so now we need to just finish this up, and we'll do a graph with our calculator on this primarily. So that's y minus 0 equals negative 1/2 x minus 4. I'm going to go ahead and just solve that for y. So y minus 0 is y. I'm going to multiply this out, so I've got negative 1/2 times x is negative 1/2 x. And then I've got negative 1/2 times negative 4, which is 4 over 2, so that's plus 2. Okay, you don't have to write that down. You can do that in your head. Any arithmetic you can do in your head is fine. So that would be the answer we're looking for, is that's the tangent line right there. Okay? Let me pause there for a second before we do our graphing calculator, because we're going to use our graphing calculator on this. Is there any question about anything I did? Okay. You're going to work with a lot of tangent lines, you know, for further applications. So what I'm going to go ahead and do now is I'm going to just put in the function and I'm going to graph it. And you can just kind of draw a sketch. You can do this with me if you want to. So let's see. What we're graphing is 2 times the square root of x and then minus x. Okay, that's a pretty good graphing calculator problem right there. And let's just do that in a standard window and get enough points. So I'm going to go zoom 6 to get that taken care of. Okay, that's kind of a weird looking graph. That's kind of cool. Okay, well, what I'm going to do is just get a couple of points on here. Now, so a good way to get a pretty accurate sketch is to go to your table. So if you go second graph to get your table to come out, there's a bunch of places this is undefined. So what I'm going to do is just have you plot some of these points. So we got like a 0.00, you got a 0.11, then you got a 0.40, and then I see one other good point. I see like 9, -3. Just get some good points, and then you got it. So that graph is kind of doing something kind of like that. Okay, does it make sense to you guys why the only values of x are 0 and bigger? What did we just graph? 2 radical x, okay? What's the domain of that function? Greater than or equal to 0, right? You can only have a number under a radical as 0 or positive, so that's why. Okay, now let's go ahead and do this. Now you don't need your calculator on this. Let's graph the tangent line. So if we graph the tangent line, we'd have a y-intercept at 2, like that. And then your slope, if it's -1 over 2, would tell you to just go down 1 and right 2. So from that point, I'm going to go down 1, right 2, and do that a couple of times. Then I'll just kind of sketch in that tangent line, okay? And then I got it right there. So what we were doing in this problem is we were looking at the equation of the tangent line at the point 40. Does that look right to you guys? I think it's a thing of beauty. It looks perfect. Okay, I'm going to do one more thing on the graphing calculator. You can do this too if you want to. I'm just going to put in the -1/2. You can put -0.5 if you want to. Now notice if you do the fraction, you better put it in parentheses like that. So I'm going to put -1/2 like that times x plus the 2 and then graph it, and that gives you the same thing. So I'm just trying to show you that that is a tangent line at 40 like that. Okay, and you can even do this. If you type trace and put 4, it'll be blinking where it's supposed to. Okay, so I can tell visually that's an outstanding looking tangent line. What do you think? Okay, all right, so technology can kind of open up a lot of this stuff up for you and help you make sense of it. Okay, all right, how's that look to everybody? Okay, now in the world of like physics and stuff, one of the things we're going to learn is like you can represent a particle's position with a function, and the first derivative turns out to be its velocity because it's a rate of how it's changing. Okay, so we'll be getting into that a little bit shortly here. Is to go through here. So this is another thing that we do quite a bit in calculus, is we can tell where a tangent line's horizontal by doing calculus. Now, the first thing I want to do on this one is, without the calculator, just to start with, without the calculator, I want to look a little bit at graphing this function. So we're going to look at the function f of x equals 9 minus x squared. Okay, now that's a parabola opening downward, right? From your background, everybody should know that, okay? Well, one thing I'm going to do on this, first of all, I'm going to find like the x-intercepts, okay? And when you find x-intercepts, you can just set that equal to 0 and find where it crosses the x-axis. That's the way you always find x-intercepts, okay? Well, you can do that by factoring, or you can do it by square root property. We can just do this if we want to. You can move the x squared the other side, making that positive. Then if you square root both sides, that's going to give x equals plus or minus 3. So what that means is, for the graph, that just means that you would have an x-intercept at the point 3, 0, and you would have an x-intercept at the point negative 3, 0. You know, it's a parabola pointing downward, so that's one way to figure out those x-intercepts. Okay, the other thing that we can do on this is we can find the y-intercept, okay? And we always find a y-intercept just by setting x equal to 0. So in other words, we just do f of 0. So if I plug in, I'd have 9 minus 0 squared, and again, I'm just replacing x with 0, so that gives f of 0 equals 9. So what that means is, if you go up on the y-axis to 9, you have the y-intercept like that. Okay, now that's one way to get this thing graphed very quickly, is just by finding intercepts. And then what you would have is you would have a parabola opening downward. Okay, and from college algebra, do you guys remember the minus flipped it in front of the x squared? What did the 9 do? It flipped, took it up 9. So that's what that did. So what we're going to do is we're going to figure out with calculus where the tangent line's horizontal. Now you can tell where that happens. So where would be a place on this graph where you would have a tangent line that's level, just by looking?
9. Y equals 9 x1.
That's 0, right? Okay. So that's what we're looking for. So remember, the idea of the tangent line right there would be horizontal. Everywhere else it would be sloping in some way, okay? So the way we can find this with calculus, I mean, it's easy to tell this one visually. What you do is you do the derivative of this function, okay? So the derivative of this one's easy, you can do in your head. Derivative of 9 is 0. Derivative of x squared is 2x to the first, or just 2x. So that means f prime of x is equal to negative 2x. Okay, that gives the function that would give the slope of the tangent line. Okay, then what you do is you want to set f prime of x equal to 0. The reason we do that is because that's what happens when you have a horizontal line, right? Anytime you have a horizontal line, the slope's 0. So what you do to finish this up then is you just say, okay, negative 2x is the derivative, set that to 0, solve the equation. So now if I divide both sides by negative 2, I'm going to get x equals 0. Okay, and that's pretty clear, I think, by the graph. When x is 0, don't you have a horizontal tangent line? Okay, so see, you can do this. Now this is a real important thing in calculus. It gives us the ability to figure out where a function has maximums and minimums. Okay, because that's what's special about maximums and minimums, is that's a place where the tangent line can be horizontal. Okay, so that's really what we found, is a maximum by doing calculus. Okay. All right, so what you do with this kind of thing, if I want you to figure out where the tangent line's horizontal, again, what you do is you just do f prime of x, set it equal to 0, and solve the equation. That's how it works, okay? All right, does that make sense to everybody? Okay, now the next problem, I want you guys to go ahead and do this. We're going to do the graph with a calculator. This is a good graphing problem right here. So what I want you all to do is go ahead and do the derivative of the function, and then set the derivative equal to 0 and solve the equation. I think this one, you probably will have two places where that happens. So go ahead and do that. Do your derivative, which you hopefully by now can do easily in your head. Set it to 0. Think you'll have a quadratic equation, and it will factor. I want to give you a few minutes to think about that to kind of check your factoring skills. And then you can put that in your graphing calculator if you want to, and just kind of approximate the graph. And then see if your answer makes sense with what the graph is going to show. The factoring, because I see problems with that. Okay, so let me go ahead and you can try to get that factored. So f prime of x is going to be negative 3x squared plus 2x plus 5. Okay, that's your derivative. Now, what you want to do is, since you're going to find a horizontal tangent line, you want to take that derivative and you want to set it equal to 0. So there's a few algebra things you may need to review on this. The way I do this is like this. Now, this is just my preference. Before I factor something, I always like to have the highest power have a positive number in front. Now, you can bypass this if you want to. So what I'm going to do is I'm going to multiply both sides by -1. You don't have to, but I think it's helpful. So if you do that, you would have 3x squared minus 2x minus 5 is equal to 0. Okay, it's just easier to factor that way. At least that's what I think. Okay, now the factoring, sometimes these problems right here cause students a lot of problems from their background. So what you're doing is just kind of reverse FOIL. You kind of do this by trial and error. So the first term is 3x squared. So that means that you would have to have a 3x and an x there when you factor that. Okay, the last term is a 5. So that means you got to have a 5 and 1. Now you may have to adjust which way you do this. So I'm going to put a 5 and 1 like that. And you do this by trial and error. Okay, so what's going to happen is when you FOIL this, that term is 5x. This outside term is 3x. What are you trying to make this add up to? -2x. Okay, so can you make 5 and 3 add up to -2? Of course you can. You have a -5 and a +3. Okay, you have to kind of do that by trial and error, and you got to get that correct. So that means that you would have to have a negative with the 5 to get the -5x and a positive there. Okay, and I suspect some of you may be a little rusty on that kind of factoring, and you need to be solid with that. Okay, do that by trial and error. Now, what you do from here is you do 3x minus 5 is 0. That will give you one place where the tangent line's horizontal. Then you do x plus 1 equals 0, and that'll give you your two answers. Okay, so when you do this, you can add 5 to both sides, or you can just move the 5 like that, divide by 3. So the first answer you should get is 5/3. That's one place. Okay, and then do this one. You can subtract 1 from both sides, or just move that so you get, these are the two answers, are 5/3 and -1 like that. Okay, so I take the derivative, set it to 0, solve the quadratic equation. Again, about 90% of that problem is algebra. So how's that algebra look? Okay, all right, get your factoring down. You're going to have to. Now let's look at what the graph looks like and see if this makes sense to us. And we're just going to do a rough graph. So I'm going to go ahead and put the function in. I'll just graph it in a standard window, so I can go zoom 6. And we're going to get a polynomial function. Kind of has a certain shape to it like this. Now what I'm going to do on this is just have you do these key points. This thing right here on a polynomial, that is the Y-intercept. So we're going to have a Y-intercept at -1. And the other things on this, I don't really care that much. Let's just kind of estimate how this goes. It looks like it has an X-intercept somewhere between 2 and 3. It looks like right around -2 is an X-intercept. And then just wing it. Okay, it's good enough on this one to just wing it. That's not the problem. It's not really what I'm after anyway. So here's kind of what I want you to see on here is we're trying to find two places where the tangent line's horizontal. Okay, one place is -1. My graph is not perfect, but does it kind of look like you would have a horizontal tangent line there. Okay, the other place was 5/3. 5/3, I think, is 1 2/3. So the other place is right there. Now, the thing that you can do visually with a graphing calculator that's real helpful is just to trace. So once you get that graph in your calculator like I've got there, if I type trace -1, okay, well, it's going to be blinking on that minimum. That's a minimum. Okay, that's a place where the tangent line's horizontal. Then if I trace at 5/3, it should blink on that maximum. So visually, you can tell you're right. You see what I mean? Okay. So the big deal with that problem is the factoring and the algebra part on that. And then visually with a graphing calculator, you can tell you're right on these problems. I want you to do that. Okay? All right? All right, any questions about anything, any of the algebra or anything? Okay, you're going to practice your factoring a lot in this class, so you want to get that taken care of. Okay, let's do this one together, and then we're going to go to a couple of different topics here. So here's a tangent line problem. So you're supposed to find an equation of a tangent line, and we're doing that at a = 1. A is really telling you just where we're looking for that tangent line. So there's two things you got to do. The first thing you got to do is you got to find what I call the point of tangency. I have to at least give you the x value, which I did. Okay, so we got to do that. Okay, so really we're looking at a = 1. So that means what we need to do is we need to replace all of the x's in the function I gave you, -3x² + 2 with a 1, and then that'll give you the y value. Okay, and that will be where we're looking for our tangent line. So that's going to be y equals -3 + 2. That's equal to -1. So what you get is your point of tangency is 1, -1. So that's the first key part of the problem. See, when I give you a = 1, I'm just telling you that's the x value of where your point of tangency is going to be. Okay, so that's what you got to do. Step 2, what you have to do on this is then you have to find the equation of the tangent line. So you have to find the derivative. Okay, so our function is y equals -3x² + 2. So we need to do our derivative. Now you can write that as dy over dx. You can write it as y prime. That's another way to do the notation. So what is the derivative of this function in your head? -6x, power rule. Bring the 2 down. 2 times -3 is that. And then the derivative of the constant 2 is 0. Okay? Now what you have to do is you have to find the slope. You're finding the slope of the tangent line. Okay, I'm going to write that as MTL for slope of tangent line. Well, and you're doing that at x = 1. Remember, I have to give you that value. So we do y prime is equal to -6 times 1. So that means the slope of the tangent line now is -6. Okay, so you've got those two things. In order to find an equation of a line, you got to know two things. You got to know a point, and you got to know the slope. Okay, we've got that now. Does that make sense? Okay. So I gave you enough information to find the point, and we did the derivative to find the slope. So what we do now is you want to write down the formula. This is the formula you're going to be working with that gives you equations of tangent lines. The only difference from what you would have done in college algebra is that slope is coming from the derivative, see? Okay, so we would have y minus the y value. Okay, just look at your point here. The y value is -1. Okay, your slope was -6. Okay, and then the x value was 1. I gave that to you right there. So those are the three things that we have. Okay, now we're ready to just solve this for y. So that's y plus 1 equals -6x plus 6. And you just do a distributive property, and you can subtract 1 from both sides. So you would get the answer is y equals -6x plus 6. So that should be the equation of the tangent line on that problem. 6 minus 1 would be what? 5. I'm recording myself too, so that's okay. It's on YouTube for everyone to see throughout the world. Okay. All right. 6 minus 1 is 5. I know that. All right. So that's the answer. Does that make sense to everybody? Okay. Now let's close this off just kind of with a quick thing on the calculator. And so we know we have I've given you a quadratic this time. So again, this is kind of a nice visual way to check all this then. So I'm going to go y equals negative 3x squared. Okay, plus 2. That should be a parabola that's upside down. It should have a y-intercept of 2. And then I'm going to go ahead in y2 and I'm going to put in negative 6x plus 5. And then we'll see visually if that looks the way it's supposed to. Okay? All right, so we got that. My parabola should come out here in a second here, and then the tangent line will come out like this. And we're looking at the tangent line at a equals 1. Okay, so the equation of the tangent line should come out there. And I'm just going to slide this over here so we can take a look at that then. Okay, and you can just make a rough sketch. It doesn't have to be perfect. Okay, just because the point behind this is that you see visually what's going on in the problem. So basically what I see is at the point 1, negative 1, not that point, this point right here, 1, negative 1, that's what we just found is the equation of a tangent line. So what do you guys think? Does that look good? That looks perfect. Okay, so that's the idea is graphically you can pretty well look at this and help you make sense out of what the calculus did. Okay, all right, so that would be the answer, and visually you can tell it's tangential to the curve at 1, negative 1. Okay, is there any questions about that? So I've done a couple of tangent lines. Those are going to be things that are kind of important to do. And you'll do this throughout the semester as we learn other kinds of derivatives and other kinds of functions. Okay, like that. All right, any question? Anything I need to clarify there? Okay. All right, now what we're going to do is what we call a higher order derivative. And some of you have asked me this question is, can we just keep differentiating? The answer is yes. Okay, if something's differentiable, then you can get higher order derivatives. And these things have a purpose. So what I'm going to show you on this is just kind of the notation. So if you see f double prime of x, that just means the second derivative. And what it means is you would just do the derivative 2 times. Okay? And then when you go beyond that, you can write like f triple prime of x is like the third derivative. Okay, like that. And then once we get past the triple prime, we quit doing that. We just start writing it like f of 4 of x. So if you saw like, that's supposed to be a 4, f parentheses 4 of x, that would mean like the fourth derivative and so forth like that. So first thing you got to know is just the notation, all right? If you do this in Leibniz notation, you might want to write this down, is like you would say like d2y over dx2. Now it's not d squared y, it looks like a second power, it's just saying second derivative. That's saying take the second derivative of y with respect to x. If it was a third derivative in Leibniz notation, it would be written like that and so forth. Okay? So what we're going to do is just do some derivatives. We're not quite ready to do applications of this quite yet, but we'll get there. So we're going to do some higher order derivatives here. Okay? And these things can get complicated, but if you're doing a polynomial, like I'm doing on these 2 examples here, it's actually real easy to do. You can do it in your head. Okay? All right, so we're going to do the first 3 derivatives of these. So let's start with number 44. I'll do 44, then I'll let you do number 45. Okay? These you'll be able to do in your head. These are easy. Okay? So the first derivative would be 9x to the second plus 10x and then plus 6. Okay, that's just using your power rule. So that's derivative number 1. When you do the second derivative, you just do it one more time. Okay, so that's going to be 18x, and then the derivative of 10x is 10. The derivative of 6 is 0 since it's a constant, so that's your second derivative. Okay, what is the third derivative? What? 18. If I wanted you to find the fourth derivative, what would you get? 0. What would be the 1000th derivative? 0. So you can differentiate forever if you want to. And on a polynomial, it eventually is going to make it to 0, okay? And it'll be there forever, okay? I'll let you guys do 45, and you can do these in your head. Just do the first 3. You don't have to go further than that. But if you do, you'll eventually get to 0 since it's a polynomial. Okay, so that's what I got on that one. So if you got your derivatives down, and if those are pretty easy to do. Okay, how's that look? Okay, what you'll find when we start looking at applications of derivatives, like in physics, the first derivative is the velocity of a particle, and then the second derivative is the acceleration of a particle, because they're rates of change. Okay, like that. That's one thing that we'll kind of look at. Okay, on the next page I want to do a little bit more of this, and then we're going to kind of go into the exponential function. That's the other thing I want to get done here today. And these right here are just, you're going to do 3 derivatives on these. So we'll do this one real quick. Okay, so, and then number 2, you have to take a little bit different approach to it. So number 1's pretty easy. Okay, you would just have 16x to the 7th. Plus 16x. What's the derivative of x? I keep asking that because students don't know that a lot of times. Minus 1. Linear term. If it's just an x, the number in front gives the slope. Okay? G prime of x. Okay? 16 times 7, whatever that is, I don't know. I'll get my calculator out because I don't know. 112, that's what that is. So that's 112x to the 6th plus 16. Okay, and you can get into some pretty big numbers. So now when you do the third derivative, you'd have to do 6 times 112, that's 672, x to the 5th like that. Okay, all right. Now, when you're doing number 2 on this, you would have to multiply it out and then proceed like I've done on the other one. Let's go ahead and multiply this one out. So we're going to have, first term, you're going to have 2x to the 3rd. Then you got to take 2x times 9. You're doing a distributive property. Then you're going to do, whoops, hold on, kind of doing that out of order there. It doesn't matter though, really. So next term, 2x times 4x is negative 8x squared. And then 2x times 9 is 18x, like that. Then you just start over again with the negative 3. So that's negative 3x squared plus 12x. And then minus 27, like that. Okay, so you got to be able to do your multiplication and be solid on that. Okay, so let's see, like terms, so I'm going to have 2x to the 3rd. Minus 8 minus 3 is minus 11x squared. 18 plus 12 is plus 30x. And then minus 27, like that. Okay, then from there you should be able to get the derivatives taken care of. Okay, all right. Okay, so now we just do this in our head. So the first derivative would be 6x squared minus 22x plus 30. See, that becomes a quadratic. Now when you do a derivative of a quadratic, it becomes linear. So that's going to be 12x minus 22. So that's a line. Okay, and then the third derivative, what's the third derivative going to be? 12, like that. Okay, so that's how that goes. So that's a kind of an example of one where you have to multiply out, and then you can do your derivatives in your head. Okay, how's that look? Okay, just trying to get the process down before we actually start doing anything with the higher order derivatives. Generally, you work with first and second derivatives most often. But in Calc 2, we have situations where we go beyond the second derivative for applications. Okay, next thing I'm going to kind of talk you through here is this idea. So what we're going to try to do is try to develop a formula for the derivative of e to the x. Okay, so I'm going to kind of explain where this one comes from. So one of the ways to help a student see this is to just look at the difference quotient. Anytime you're developing a derivative formula, you got to go back to that definition of a derivative. Okay, so what I'm doing on this is I'm looking at f of x equals b to the x, and I'm going to go ahead and let's put that in the difference quotient. Okay, so if I do that, f prime of x would be the limit h goes to 0. Remember, it's f of x plus h minus f of x all over h. So that's going to actually be b to the x plus h minus b of x all over h like that. Okay? So and basically I'm not going to finish that because it can get a little bit tricky when you do that. But what I'm going to go ahead and do on this is I'm going to look at f prime of 0. So I'm kind of interested in what's happening at 0 on this. So I'm going to replace all of the x's with 0 before I look at this limit. So I've got the limit as h goes to 0, and that would just be b to the h, okay, with that going to 0. Then that would be b to the 0 over h. So that would be the limit h goes to 0 of b to the h, whoops, I'll write that better, b to the h minus 1, because anything to the 0 power is 1. So I'd have that. Okay, now this is just kind of to get you, kind of showing you what I did on the calculator. You don't need to get your calculator on this. I just want to talk through what's happening. Okay, so what would happen on this if I looked at different powers? Here's the idea. So like if I looked at b is equal to 2, if I put in my calculator this thing, like if I put in like 2 to the x minus 1 over x, and if you just kind of traced out various values of h, when h is getting close to 0, that's the idea, what's happening is that value of that limit's getting close to that, and so forth. If you went on to b equals 3, and you graph that in your calculator, you'd be getting close to that. Okay, and so forth. Well, one of the things that's kind of happening on this a little bit is as e, what we're going to kind of look at on here, and then I'll talk about this on the next page, e is about 2.7, then it's a repeating decimal. Okay, so e is like an irrational number like pi is, so it's about 2.7. So what's happening is if we let b equal around 2.7, this limit would have some sort of a value like right there. So it's approaching some number. So what I'm trying to show you on this is just sort of graphically is where this value of this thing would be approaching. Okay, then on the next page I'll formalize it a little bit to you then. Okay, so what we're kind of looking at is using a table trying to figure out where this limit's going. Okay, does that make any sense? Okay, it will. I think it will on the next page. Okay, all I want to do is just give you a rough idea on that anyway. Okay, so here's the idea. All right, now let me kind of show you what I was trying to show you on that is if you used e instead of 2 and 3, it would go to 1. Now I want to back up on my page here a little bit and show you that idea and just see if this kind of makes sense to you. See, e is 2.7 approximately. So it's a little closer to 3 than it is to 2. If you look at this thing right here, doesn't that thing look like it's heading to 1 kind of? Or getting close to 1? So if you actually, instead of doing 3 to the h, if you did 2.7 to the h, it would get closer and closer to 1. So what I was trying to show you with that is we're getting close to 1. The value of that limit's close to 1, just visually. Okay? So what we're going to end up having then is this is the number e, and that's just a lot of the decimals, so it satisfies this limit. That's not a proof, that's more of a demonstration with technology that that limit would be approaching 1. Now what I want to show you down here is I want to go through this kind of proof of what the derivative of e to the x is. Now you don't have to write anything down. I just want to kind of talk through this and see how much of this makes sense to you. So what I'm doing on this is the difference quotient. Okay, that's like, remember, f of x plus h minus f of x over h. That's what I've done right there. F of x is e to the x, and then f of x plus h is e to the x plus h, right? Okay. Now I want you to look at the algebra on here and see if you understand what's going on with this proof. Okay. What I did is I took e to the x plus h and I broke it up into that. Can you do that? Is that valid? Yes, because whenever you multiply, you add exponents, right? I mean, e to the x times e to the h is e of x plus h. Okay. Then I factored an e out. So if you factor that e out, you would get e to the x times e to the h minus 1. Just multiply that out in your head, and you'll see that's right. See, that's e to the x times e to the h, and e to the x times 1 is e to the x. Okay, does that make sense? Okay. Now here's the thing. Okay, when you're doing a limit as h goes to 0, that variable x can be treated as a constant because it's a different variable. So I pull that out, and that leaves me basically with this. Okay, that leaves me with this piece right here, and that's equal to 1. That's kind of what I was showing you on the previous page when I did all that calculation with the decimals. That got close to 1. So the idea is that thing just comes down, and then this thing right here is 1. So what we just show, and this is what you're after, is the derivative of e to the x is e to the x. Okay, that's the simplest derivative there is. Okay, it just turns out to be a function where the derivative is the same. Okay, that's what's special about e to the x to a mathematician, is it has that special characteristic to it. That's what makes e such a special number. Do you guys kind of see what I did on this? I don't know. I kind of go through a proof and those people kind of like start rolling their eyes at me and stuff. Okay, I just want to give you the idea. Can you kind of follow the logic on that? Okay. All right, so here's what you want to know is that. That's what you're required to know. That's easy to remember, right? So whenever you do a derivative of the exponential, then it's itself, okay? That's kind of where the proof comes from, is that idea, okay? Okay, so let's see. To finish this up, we're going to do, there's a couple other things I want to look at here. And this problem right here, you'll have something in your homework like this. This is actually a good problem to give students because it helps you understand derivative rules. It sort of tests you on derivative rules. So what we're looking at in this is y equals f of x. That black graph right there is the graph of f of x. Okay, and then the graph of g of x is the one that's in red like this. And what you've been defined here is you're defined that f is equal to the sum of two functions, f plus g, and then g is defined to be 3 times the function f minus g. So we're going to do these problems. We're going to do capital F prime of 2. Okay, and we're going to do that by looking at the graph. The purpose of this is that you can interpret a graph correctly. Okay? Okay, well what this means is, what we're really doing is capital F is defined to be f plus g, little f plus g. So what we're going to do on this is we're going to do the derivative, and I'm just going to write this, let's write it like this actually. We can write it like this, okay? You can say f of 2 plus g of 2 prime, the whole thing derivative like that. You can write it that way, okay? You're doing the derivative of that. And what I'm doing is I'm replacing capital F with what it's defined to be. It's f plus g, okay? Now, what we learned is, and we learned this rule, if you have a derivative of a sum, what you're allowed to do is you're allowed to do the derivatives, then add them together. So that's the key to doing the problem, is to look at it that way. Okay, that's a derivative rule we learned, and we've been doing all class period. Derivative of sum is sum of derivatives. Okay, so what we're going to look at on this then is as we go through this now, we want to just try to figure out what the derivative is graphically, okay? So you want to look at this kind of carefully on here. Is let's look at f prime of 2. So what you do is you go to this function f at 2, and let's just kind of put a dot on there, and let's see if we can figure out what the slope of the tangent line is right there, okay? Now, since let me stand up and kind of show you what my thought process is on this right here. Okay, what's a tangent line to a line? It's already a line, right? What's the slope of that line right there? Let's count it out. Looks like down 3, right 1, right? Okay, so that slope looks like that would be -3, all right? Okay. Now you want to do the derivative of g prime of 2. Well, look at g prime it's on this line. Okay, so what's the slope of this line? Let's see, what do you think? Up 1, right 1, up 1, right 1. So that's what it looks like is when x is 2, it looks like the slope of that's 1. Okay, so you're looking at a slope of the tangent line, and that's how you would work that out then. Okay, so again, this one, if you look at this piece right here, f prime of 2 is going to be the slope of this line, which we said is down 3, right 1. So that's just -3. And then g prime of 2 is going to be the slope of the red line right here, right there. That looks like that's going to be up 1, right 1. So that goes like that. So that means the answer is going to be -2. Okay, does that make any sense? Yes, okay. And the reason you're able to do this is because I'm giving you functions that are lines anyway. So you can find the slope pretty easily by doing that, okay? These are just good thought problems is mainly what they kind of get you to think through concepts good. Okay, let's do g prime of 2. Okay, well, first of all, what g prime is g prime is, g is defined to be 3f minus g. So what I'm going to do is I'm going to just change this to 3f of 2 minus g of 2. Then I'm going to do the derivative of the whole thing. That's a good way to write that out, is like that then, okay? So the next thing is you got to know your derivative rules. So what we learned is when you do a derivative of a difference, you can just do the difference of the derivative. So this would just be 3f prime of 2 minus g prime of 2 like that, okay? And that constant 3, we learned that a constant is independent of that variable. You just write it in front. Okay, now we've already got these things figured out then. So we said that f prime of 2, when x is equal to 2, you're at that point right there, the slope right there is equal to -3. Okay, so that's -3. At g prime of 2, we're looking really at this point right here, and that slope right there is up 1, right 1, so that's 1, so it looks like that's -9 minus 1, so that's equal to -10 like that. Okay, and then that's the idea. Okay, does everybody follow that okay? Okay, all right, let me run through one more here. So we're going to look at capital F prime of 5. Okay, so if I look at this, F is F plus G. So we're going to write this as F of 5 plus G of 5, and then we're going to take the whole derivative like S. So now we're just looking at a different point on the line right here then, okay? So what that's going to be is F prime of 5 plus G prime of 5, like that. Now we just need to shift our focus to 5 now. So if you're looking at F prime of 5, you are here. Okay, right there. Okay, am I on the right graph? Yeah, that's F prime. What's the slope right there? That's 1, right? Okay. Now look at G. Okay, G would be this point right here. Okay, what's the slope of that line? Down 1, right 1, so that is -1. Okay, like that. So what you're doing is you would have 1 plus -1, so that means that one is going to be 0. Like that, okay? So you're looking at a slope of a tangent line to a line, so what's the slope of the line anyway, okay? And then this activity, what it forces a student to do is to understand basic derivative rules, okay? You guys get what I did there? Okay, it's just a concept problem. It just helps students learn concepts. That's the purpose behind that. Okay. Okay, last thing I want to look at is this kind of thing with a table, and then we'll finish up this section with a couple of things we'll do on a calculator. Okay, these are also pretty good examples of how you can take a table and look at a derivative. Again, this forces a student to learn their derivative rules. That's the purpose. So what this one is saying is find the derivative of f of x plus g of x when x is 1. So what we do is the rule we learned is when you do a derivative of a sum, that's the same thing as the sum of the derivatives. So that's the rule that you must apply. Okay, now we're evaluating at 1. So you're just replacing x with 1. So you're looking at f prime of 1 plus g prime of 1 like that. Okay, now you just look at your table. So the other purpose of this is, can you read the table okay? All right. So if you look at my table, it says, okay, f prime of 1 is equal to what? 3. That's what that says. So that's equal to 3. Okay. Then g prime of 1 is going to be 2. Okay, that's the g prime row, and just kind of looking at the row and column. So that's going to be equal to 2. So that means the value of that is 5, like that. Does everybody understand that? Okay. The table gives you the values of the derivatives at the different points. That's where you get it. So you're doing this indirectly.
Will you always give us to define the derivative kind of function?
Yeah, I have to. Now, on a problem like this, the purpose is you're showing me that you understand derivative rules. Okay? Because a lot of times when you're just doing a derivative, you kind of bypass the rules a lot. That's what the purpose behind this is. Okay, this one you're doing a derivative of 1.5x. Now what we learned, the rule we learned, is a constant comes out of our derivative. So you just write this as 1.5 times f prime of x, like that. And then again, you're just evaluating this at 2. So really I should just write this as 1.5 f prime of 2. Okay, the idea is 1.5 is not a part of the derivative. You want to look up what f prime of 2 is. Okay, look at the chart. Tell me what f prime of 2 is. 5. There's 2. There's f prime. You're at 5. Okay, so the answer to that would be 1.5 times 5, whatever that is. What's that? 7? 7.5? Let's see, that'd be 5. Yeah, that's 7.5. Okay? Okay, that's the idea. Okay, and the next one, okay, the idea with this one is you're doing a derivative of a difference, and you can write this way. You can just write this all in one step. If you do this derivative, you're doing the constant times just x. Now that's just x, okay? Now you have to do the derivative of that, and let me write this like this. Let me kind of write the step a little bit better on this. So I'm going to write this just as the derivative of 2x, which we'll do, minus 3 times the derivative of g of x, and then we're going to evaluate that at x equals 4. Now you can do a lot of this stuff in your head. It's kind of like the limit laws that we learn. So it kind of goes like this. Okay, what's the derivative of 2x? 2. Now see, I'm telling you to do the derivative of 2x. Okay, now what you have is you have 3 times. When you do the derivative of g, that's going to be written as g prime, and then you're evaluating that at 4 like that. Okay, so you're doing that. You take the derivative of 2x, then you can look up in your chart what this thing right here is. So what is g prime of 4? 1, right? Okay, you got the column of 4, the row of g prime, that's going to be 4. So it looks like you would have 2 minus 3. And there's your value of g prime of 4 is right there. That's 1. So it looks like that's going to be 2 minus 3. So that's equal to -1. Like that. Okay? It's arithmetic, but it's mostly knowledge of your basic derivative rules. Is there any question about that?
How come when I take the derivative of -3?
Because it's a constant. Okay? So remember, like if you had something like the derivative of 3 times x to the third. Really what you do is you just write the 3 down. And then when you do the derivative of x to the third, that's 3x squared. So I don't do the derivative of the constant, I just write it down. That's what the derivative rule told us to do, see. Okay, you just ignore the constant and write it down. Now what you guys are kind of trained to do now is, you know in your head that'd be 9x the second. But technically you're just writing the constant, then multiplying by that number you bring down. Does that make sense? Okay. Okay, let's look at a couple of things on the calculator. So you want to get your calculator out. I do want you to know how to look at a few limits here and there with a calculator. So let's finish up with this here. Then we'll start the product and quotient rule today. Okay, so some of these are kind of interesting. I gave a couple of these, I think, on the homework. I think I even gave that number 67. I think you'll see that same thing on your homework. So let's put this in. So the first one, we would have to type it in like this. We'd have to have parentheses. When you do e, you can go second ln to get the e to the x to come out. Like that. So I'm going to put my variable in like that. And then minus 1. Whoops, I got to put a 3x in there, don't I? Whoops. Yeah, and you got to have that in parentheses, that numerator's in parentheses. So you go e to the 3x, go like that, and then you got to get out of that exponent, minus 1, and then we'll divide by x like that. And we're just going to do this in a standard window. We'll zoom in if we need to, so you want to kind of start like that. Okay, so if I do that, let's just, once you get that in, let's go zoom 6 to just go a standard window. And we're going to look at the limit as x approaches 0 and just see visually if we can kind of figure out what it might be. Well, so one thing I'm going to do on this one, I'm going to slide this graph over here and just kind of see what we have here. First of all, what you'll see on this one, on number 65, is there's kind of a break right there, right? How come? Okay, you're undefined at 0, right? So there is something going on there. There's probably a bubble or something like that going on there. Okay, that's what I'm seeing on my calculator. So if you were going to look at this one with your calculator, this kind of goes back to what we saw in the past here, is if you went through and traced a little bit to the left of 0, like at, say, something like 0.001, okay, you would get some value that's getting pretty close to 3, isn't it? So it looks like that's getting pretty close to 3. If you traced at a number that's barely bigger, that's positive than 0, like 0.001, looks like you're close to 3. Okay, so you could conclude on this problem that it looks like, just if you look at this analytically with a graph, that that's going towards 3. Okay, now what's happening on this thing, there's 3 right there. You have some kind of a discontinuity right there. Okay, that's the idea, right? Okay, does that make sense? Okay, these are pretty hard limits to do without your calculator at the stage we're at right now. A little later we end up learning something that's called L'Hopital's rule, where you can do derivatives and limits and you can do it analytically, but for now you have to look at your calculator. Okay, so that's 3. Okay, try the next one. The next one's awesome. I love this one. I already know what the answer is. So let's try this one, okay? And see if you recognize anything on this. We'll put in 1, and you got to put 1 over x. Use the variable x. So 1 over x. Close the parentheses. Then raise to the x power like that. So it has to be put in like 1 plus 1 over x to the x. And then I'll just start this in a standard window, and I'll probably have you change a couple of things on this one. Okay, so if you get that put in, you go zoom 6, it'll kind of look like it might have a horizontal asymptote or something. Okay, so let's see, it kind of does something funny like that, and it kind of does something like that. Okay, one thing that's happening on this one is you're undefined at 0. You can't have a 0 denominator, so you kind of have that going on like that. Okay, now I'm going to slide this over here and I'll show you kind of what I want to show you on the calculator here. Okay, well we're interested as n goes to infinity. So let's just kind of go with some pretty big numbers. Let's go trace at 6, for instance. Okay, we're at about 2.5. Now I'm just going to keep going out with my right arrow key, and that thing's getting a little bit bigger as I go. It looks like it's leveling off, but it's going somewhere. 2.5. Okay, now I'm going to do this. Now you don't have to do this, you can just watch this. I'm going to make my window go from 0 to 1,000. And see if you see what I want you to see. 0 to 1,000, maybe scale by 100. And then for Y, I'm going to go 0 to 3. Okay, because I already know what's going to happen. Okay, then you can do that with me if you want to. So you can tell it's leveling off. You can tell the graph has a horizontal asymptote on it. So if you kind of changed that window to like that, now if I regraph this, let's see what's happening as we get to 1,000. Well, it's leveling off, and let's see if you catch what I want you to catch on this then. Okay, so let's trace at, let's say something like, let's just go all the way to 1,000. Well, there's 500 right there. At 500, the value is 2.7. Does 2.7 mean anything to you? It's E, exactly, okay? So as this thing is going further and further out, it's just getting close to E. And the decimal accuracy is increasing on that. So that actually goes to E. That's the definition. That's one way to define E, is you can define it in terms of an infinite limit, okay? So that one really is going to give you the value of E on that. Okay, so the idea is it would just be approaching E. Now one thing I can show you on this also is if I go to Y2 and I just put the letter E in, okay, the letter E is like above the division symbol. So if you go Y2 and then just put in E, but not that, it's got to go like this, got to go second division symbol and then graph that, well then you'll see that it's an asymptote. Okay, so that's really what the definition of E is. It's that limit right there. Okay, that's kind of interesting, don't you think? Okay, that's approaching E. And by the way, there's one that you can do for pi. In Calc 2, we learn about what's called an Arctangent Series, which is one place where you can get all those decimal expansions of pi. Okay, so it shows up. Okay, x to the x. Let's take a look at that one, and then one other one here, and then that'll kind of finish this up. And these things, you're going to relearn how to do these a little bit later in this chapter with something we call L'Hopital's rule. So this one, x to the x power, that's kind of an interesting idea. So we put in x raised to the x. You got to put that in like that. Let me take the E out of there now and start it in a standard window and see what happens. So this is kind of a weird one. You're taking a number and raising it to the same power like this. So I'm going to start by going zoom 6 like this. And it looks like, and we're doing the limit on this one as x goes to 0. Now that's a right-hand limit, I think, on my handout right there. Okay, so first of all, what happens on this one, and this one's really weird. I don't want to go too much in depth with this, but when you're looking at this graph from the right-hand side, you can tell visually where it's going. So one thing you could do is if you traced at like a number barely bigger than 0, like 0.01, it looks like it's going where? 1. It looks like it's heading towards 1, okay? Now what's interesting about this problem is notice that there's no negative values there. Although what's weird about this one, and this is something that's kind of worth thinking about outside of class, if x was -1, there is an answer to that. If you do -1 to the -1 power, that's actually just, what that means is what happened to my pen? Let me close that and reopen it real quick. So if you did this like this, oh, come on, OneNote. Well, close it again and try again. Got no connection now all of a sudden. There it goes. Okay. All right, so if you did this, you would have like 1 over negative 1 to the 1. So that's negative 1. Okay, there is a value there. The calculator's not showing it. If you did something like negative 2 to the negative 2, look what happens. You would get 1 over negative 2 to the second. That's 1/4. So it jumps around wildly. It's really weird on this. What you'll kind of find on when you're doing the negatives is when that's an even number, okay, then it ends up being positive. That's a positive result. If that's an odd number, that ends up being negative. So it jumps around like crazy. So it's kind of weird what's going on in here. There are values there defined to be there, and it just sort of jumps around. So that's weird. Okay, that's kind of worth thinking about outside of class if you want to. But the value of that's going to be 1. Okay? All right, let's do one more, and then that'll kind of close us off here. So let's do 1 over x to the x and see what this one looks like. All right, so you put this in like this. You would go 1 over x, like that. Then you would raise that to the x power. And we can just start by a standard window. We're doing a right-hand limit on this one, I guess. Again, so let's see what this one looks like. You're going to be undefined at 0. And I'm going to do like a zoom in. You can go zoom in if you want to, which is option 2. Just so we see it a little better. That's all I did. So what does it look like the right-hand limit is? Probably 1. Okay, we can just try. Let's go trace a number a little bit to the right of 1. So that's going to give something about 1. Okay, so that looks like that value right there is going to be heading towards 1 from the right-hand side. Okay, and that one is undefined at 0. Then it levels off at the x-axis as you go towards infinity. So those are some kind of interesting graphs that you see a little bit there. At this stage, these things can only be done with technology. But once we get, in a couple of sections later, we learn what's called L'Hopital's rule, then you start working with these things more analytically. Okay? So I just wanted to kind of give you an idea before we get to L'Hopital's rule. Okay? So that's the only way at this stage that you would be expected